Alrighty, on to section 1.3, which in this section we're still going to be dealing with exponents, but more specifically we're going to be dealing with rational exponents. If you think back to the first section, we said rational numbers could be written as fractions, or if they were decimals, they stopped or they went on forever. So 3 objectives. We want to simplify square roots, and we'll look at the connection with exponents that they have. We want to perform operations with square roots and even higher roots, so like cube roots, fourth roots. And then we want to simplify rational exponents. This business with rational exponents and square roots is going to be a big part of one of the units down the road. So we're going to get the basics down. What I'd like to do before talking about simplifying square roots is just to go over and make a list of some of the more common perfect squares. So 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. So I'm going to keep filling this out here. So obviously these are not all the perfect squares. We could keep listing them forever, but these are the more common ones that we will run into. For sure, you should be familiar with 1 through 10. So any of these numbers that I wrote down in red are called perfect squares because, for example, if I took the square root of 16, the answer would be 4. So when I say a perfect square, I mean the numbers that I can square root and get a nice whole number out. For example, 7 is not a perfect square because there's no whole number times itself that will make 7. But if I said the square root of 144, that's a perfect square. That answer is 12. So we'll want to have this list handy today as we go through the notes. So let's try some examples. Evaluate. The square root of 64. Well, 64 is one of our red numbers. The square root of 64 is 8. Next one, a negative square root of 49. Well, 49 was one of our red numbers, the perfect squares. So the square root of 49 is 7, but if you say just 7, you're going to be wrong. Technically, that negative out front carries down, and it's still sitting with the number, so negative 7. The next one, the square root of 1/4. If the fraction scares you, I know fractions can be intimidating to people, there is a property that says you can treat it as 2 separate square roots. So the square root of 1 is 1, that's one of our red numbers, and the square root of 4 is 2. Okay, the next one, we would want to do something before square rooting, and that would be to add them. So I get square root 25, and now I want to take the square root. And it's a perfect square, 5. Now, the next property is different. I cannot add those together because they are each their own separate square root. So all I can do on this one is simplify each and then see if I can combine them. So the square root of 9 is 3, the square root of 16 is 4, and I get 7. See how these two, I put them next to each other on purpose. They look similar, but they gave me very different answers. All right, this next set of examples is something we are going to run into a lot, especially in a unit coming down the road, being able to simplify square roots. So, people can sometimes have a hard time with this. So the square root of 75, if I look at my list of red numbers here, 75 was not one of them. 75 is not a perfect square. However, there is a perfect square that will divide into 75. So what I would do is I would start checking, does 4 divide into 75? No. Does 9 divide into 75? No. And I would keep trying them, and it turns out 25 will divide into 75, and 25 is a perfect square. So to simplify this, what I tell people is we can break it up into 25 and 3. 25 times 3 is 75. So focus on the one that is the perfect square, which is the 25. The square root of that is 5. I can't do anything with the 3. 3 is not a perfect square, so it stays square root 3. So my answer is 5 square root 3. All right, next one. What we can do here, if it's easier, and I think it will be, I can multiply them together. Kind of like in the previous lesson, if we had 5x times 2y, we wrote that as 10xy. If they're both square roots, I can multiply them together. So I would get the square root of 50, and then when I do x times x, remember I add the exponents, so I get x squared. Now let's see if we can simplify it. Well, 50, not one of my perfect square numbers. So I would want to see if I can find one of these that will divide into 50. And the one that should jump out to you is 25. So I could write this as 25 times the leftovers. 25 times 2 is 50, and then we still have the x squared. Well, focus on the perfect square, so that becomes 5. And here's the leftovers. And technically, one other thing can be done to simplify this. I can't do anything with the 2. It can't be broken down any further. But the square root of x squared is x. Because the whole purpose of a square root, the answer to a square root says, hey, what times itself gives me this? So the square root of x squared is just x, because x times x is x squared. So there's my answer. Okay, next one. Again, if the fraction terrifies you, let's write it as 2 separate square roots. And now let's do each. Square root of 100, is that one of my perfect squares? Indeed it is. So that becomes 10. And the square root of 9 is one of my perfect squares, 3. So this answer is 10/3. Okay, and now the next one, this one looks messy. However, it's similar to this one where we did the multiplying. We multiplied them first and then simplified. It also works with division. So if I go the other way, if I think of this as one big square root, and I'm going to divide them, 48 divided by 6 is 8. X cubed divided by x, remember that's technically x to the first. What do we do with exponents when we're dividing? Should say subtract. So 3 minus 1, I now have x squared. Now let's see if we can simplify that. So 8, square root 8. 8 is not one of my red numbers. It's not one of the perfect squares. But I would want to see if one of these perfect squares goes into it. 4. 4 will go into 8. So I'm going to break this up with 4. And then the 2 and the x squared are left. 4 times 2 is 8. So then I'm going to focus on the one that is the perfect square, and that becomes 2. And the square root of x squared can be x. And then we still have the other 2 left over. So it would be 2x square root 2. I would also be okay, like on this second example we did, if you wrote it like this. That's the same thing. 5 square root 2 times x. I don't care where you put the x. All right. Now let's look a little bit more at adding or subtracting. The only catch with adding or subtracting radicals, which, by the way, if I haven't mentioned it, when I say radical, that's this symbol. In order to add or subtract radicals, they must be, think of them as like terms. Kind of like in the previous lesson when I had this, 4x plus 8y, I said you had to leave it because they weren't like terms. But if I would have had this, 4x plus 8x, well, I could say that's 12x because they were like terms. It's the same thing with radicals. So add or subtract is indicated. I have 7 square root 2's plus 5 square root 2's. Since they're like terms, they're both sets of square root 2's, I can add them. 7 of them plus 5 of them, I'd have 12 of them. And there would be my answer. We'd want to check to see if this can be simplified, but there are no perfect squares in 2 besides 1. Next one. I have a square root 5x minus 7 square root 5x. Yes, they're both square root 5x's, so I can subtract them. Technically, there's a 1 here. So 1 of them minus 7 of them. I should have negative 6 square root 5x. Next one, 7 square root 3 plus square root 12. I cannot combine these because one is a set of square root 3 and the other is a set of square root 12. However, the warning bell that should be going off, this guy, if I look at my list of perfect squares, 12 is not one of my red numbers. But one of these perfect squares will go into 12. 4 is the biggest perfect square that will divide into 12 nicely. So let's simplify that. I'm going to bring the first guy down. So I'm going to break this into 4 and 3 because that makes 12. Focus on the perfect square and let's simplify it. So 7 square root 3 plus 2 square root 3. I can now combine them because they are both square root 3's, so I would get 9 square root 3. Okay, so some of them you might have to simplify first. Oh boy, look at this next one. Currently, the first thing you should think is, I cannot subtract them because they are not like terms. But we can do some simplifying. So 50 is not a perfect square, but if I look at my list, I want to find the biggest red number that will go into 50. And hopefully you can spot that it's 25. So we're going to break this guy up into 25 and 2x. Let's simplify this first, then I'll work with the back one. So focus on the perfect square, the 25. That would become 5. And these multiply together. So 4 times 5, 20, and then the leftovers, square root 2x. Okay, now I'm going to do the back one here, and I think I'm going to have to write it down here because I'm running out of room. 32 is not a perfect square, but if I look at my list of perfect squares, I want to find the biggest red number that will divide into 32. You might say, oh, the perfect square of 4, but I'll tell you there's one higher than 4, and it should be the 16. So I'm going to think of the 32 as 16, and then times 2. 16 times 2 is 32. So if I focus on the perfect square of 16, that becomes 4. And then I still have the 2x. I can multiply, and I get 24 square root 2x. Okay, I'm not done, because now I have, here was the red one, and there was subtraction in between them. Since they are now both square root 2x's, I can combine them. So 20 of them minus 24 of them, I should get negative 4 square root 2x. That's my final answer. All right. There is some types of math, especially in the higher math classes, where they ask you to do something funky called rationalizing the denominator. If you rationalize the denominator, basically you want to, in a sense, eliminate the radical symbol. You want to get rid of it. Some answers are easier to work with if they don't have a square root in the denominator. So that's what we're going to try and look at here. So this first one, I have 15 over square root 6. I'll tell you, to rationalize a denominator, it's very easy. All you have to do is we are going to multiply it by itself. And in a moment, I'll tell you why that works. But there is a golden rule in math that says, hey, if you do something to the bottom, you have to do it to the top as well. So if I give the bottom a square root 6, I also have to give the top a square root 6. I got to keep it balanced. So up top, I would have 15 square root 6. They just multiply together. On the bottom, 6 times 6, I'd get square root 36. And the whole reason why it works just to multiply it by itself is because it turns into a perfect square. The square root of 36 is 6. And the last thing that I would want you to do is to simplify your fraction if it can be. We can simplify the 15 over 6. What is the biggest number that goes into 15 and 6? And it would be a 3. So my fraction would simplify to 5 over 2, but I still have square root 6 up top. Okay, so hopefully you can figure out this next one. If I want to rationalize the denominator, I am going to multiply by square root 8. But if I do that to the bottom, I'm also going to do it to the top. So we get 12 square root 8. And on the bottom, I would get square root 64. And the whole reason why we did that is that's now a perfect square. Square root of 64 is 8. And then I would like you to simplify the fraction. What is the biggest number that goes into 12 and 8? And that would be 4. So 4 into 12 would be 3. And 4 into 8 would be 2. Now there's an unfortunate side effect with this one. We're not actually done because it's not simplified all the way. Because this square root right here, square root 8, can be simplified further. 8 is not a perfect square, but if I look back at my list, there is one of these red numbers that will divide into 8 and we can make it simpler. And hopefully it's the 4 that's standing out to you. So we're going to go further with this. So I'm going to break down that 8 into square root 4 and square root 2, because that makes 8. So the square root of 4 becomes a 2. So I'd get 6 square root 2 over 2. And that divides to 3 square root 2. Okay. Cross this one off. We are not messing with that type. All right, the next item, I want to simplify. Now, these are nth roots, meaning they might be cubed roots or fourth roots. So if you look at this problem, it is the cubed root of 24. So now instead of perfect squares, I'm thinking in terms of perfect cubes. Why don't we quick make a list here? 1 cubed is 1. 2 cubed is 8. 3 cubed is 27. 4 cubed is 64. I'm not going to go higher than that. So those are some perfect cubes. It's the same process we were doing with the squares, just cubes. So 24 is not a perfect cube. It's not in my list. But is there one of these perfect cubes that will divide into 24? Yes, 8. So I could break this up into the cube root of 8 and the cubed root of 3 because 8 times 3 is 24. And then I want to focus on the perfect cube. The cube root of 8 is 2 because that says what number times itself 3 times is 8? It's 2. And then I have the leftovers. There would be the simplified form. It is the exact same concept, just with cubes. The next one. Now this one is the fourth root. Let's make ourselves a little list here. 1 to the fourth is 1. 2 to the fourth is 16. 3 to the fourth is 81. You could keep going. I think that will be fine with those. So I'm going to multiply them together first because they're both fourth roots. And I get 32. 32 is not one of my perfect fourths because it jumps from 16 and then it goes to 81. But there is a perfect fourth that will go into 32. So I'm going to break it up into 16 and 2 because that makes 32. And then I want to focus on the perfect one. The fourth root of 16 is 2. Because that's asking what number times itself 4 times is 16, 2. And then the leftover radical. Okay, next one. If the fraction throws you off, we'll do it just like we did with square roots, where I'll break it up into 2 problems. And then we'll tackle each. The fourth root of 81, is 81 a perfect fourth? Yes. It's 3. The fourth root of 16, is 16 a perfect fourth? Yes. It's 2. And that one's done. They were both perfect. And the last one here, just like with square roots, if we're adding or subtracting, they have to be like terms. So these are cubed roots, so let's look at our list of perfect cubes. 16 is not a perfect cube root. It's a perfect fourth, but I'm dealing with cubed roots. Is there a perfect cube that will go into 16? Yes, the 8. So let's say 5, cube root 8, cube root 2, because 8 times 2 is 16. Let's simplify that first. So the perfect one, the cube root of 8, becomes 2. So 5 times 2, I get 10, cubed root 2. And then I still have minus the 11 cubed root 2. They're both like terms, so I can subtract them. 10 of them minus 11 of them would be negative 1 cubed root 2. Or you could just say negative cubed root 2. You don't have to have the 1. Okay, so even if they're a cubed root or a fourth root, the process is the exact same. You're looking for the perfect ones. Okay, almost done here. The last part of today are rational exponents. And again, rational means if I really wanted to, I could write them as fractions. I always tell my students, remember, rational, fractional. It's probably not good English, but it does end up sticking. So all this means is if I have a number raised to this exponent, a fraction exponent, it can be rewritten in radical form as the radical of the number, the bottom number, which I'll do in blue, becomes the root. That didn't work very well there. So the bottom number becomes the root. So a cube root, a fourth root, a square root. And the top number, which I'll trace in green, is the exponent that it's raised to. Mathematically, these are the same exact answers. So let's try some examples so I can show you what I mean by that, because it almost looks like another language here. So simplify. 64, that didn't run off very well. It's 64 raised to the 1/2. Well, that's kind of hard to figure out what are they asking me to do there. So let's rewrite it in radical form. So when I rewrite it in radical form, it's going to be the radical of 64. The bottom number, the 2, is the root. And the top number, the 1, is the exponent that it's raised to. So what this is asking for, you really don't need the 2. This is a square root of 64. Is 64 a perfect square? Yes, the square root of 64 is 8. And then it's raised to the first power. Well, that's still 8. So this answer is 8. 64 to the 1/2 is the same thing as square root 64. So 8. The next one, 125 to the 1/3 power. Let's rewrite it in radical form. Oh, my computer is freezing on me here. Okay, there we go. So let's rewrite it in radical form. Maybe. All right, sorry about that. I had to recharge my stylus. Moving on to the next one. Let's rewrite it in radical form. So the bottom number is a 3, so this is a cube root, and then the outer number is the 1. So the cube root of 125, is that a perfect cube? If we look back, well, if we look at our list of perfect cubes, we went to 4 cubed, and that was 64. I will tell you that 5 cubed is 125. So yes, 125 is a perfect cube root, and it will become 5, and then it's still to the first, which is 5. Okay, let's try the next one. A negative 16 to the 1/2 power. Let's rewrite it in radical form. So the 2 is the root, so this is a square root, and it's raised to the first, but don't forget, I'll do it in a different color here, the negative is still there. It's going to carry down. So the square root of 16 is 4. To the first is 4, but that negative is still there. So this answer is -4. Now notice this time the -27 is all in parentheses and the whole thing is raised to the 1/3. So when I rewrite it in radical form, the negative will be under with the 27. Before it was on the outside because there were no parentheses. It's going to be a cube root because the bottom number was a 3, and then it will be raised to the first. So the cube root of 27, 27 is a perfect cube. If you look at that list, it's 3, but it's going to be a -3. If you think about it, that makes sense. -3 times -3 is 9, times -3 again is -27. To the first is still -3. And then we have 64 to the -1/3. Ooh, we have a negative exponent. So remember in the previous section, if we had a negative exponent, we would turn it positive by moving it to the other side of the fraction. So now it's a positive 1/3. Now let's rewrite it as a radical. So cube root, and then the 1 on the outside. Cube root of 64, is 64 a perfect cube? If you look at the list, yes it is. It's a 4. Then it's still to the first. And 4 to the first is 4, so this answer is 1/4. Okay, moving on. A couple more simplifying problems. 27 to the 2/3 power. Let's rewrite it in radical form. So it's going to be 27. The root will be 3. That's the bottom number. And this time, it's going to be squared at the end. The cube root of 27, is 27 a perfect cube? If you look at your list of perfect cubes, yes it is. It's 3. But then it's going to be squared. 3 squared, this answer is 9. Next one, let's rewrite it. This is going to be a square root. When it's a square root, you don't have to put the 2 there. If no number is written in as the root, it's a square root. So the square root of 9 is 3. It's a perfect square. But then it's going to get cubed. So 3 cubed, I get 27. Next one, 81 to the negative 3/4. I have a negative exponent, so first, let's move it to turn the exponent positive. Now let's rewrite it in radical form. Now this one's going to be, the bottom number is a 4, so it's going to be a 4th root. And then it's cubed. The 4th root of 81, is 81 a perfect 4th? Where did I put that list? It is. See our list? 81 is a perfect 4th, so it's 3. But then it still has to be cubed. 3 cubed is 27. So the answer is 1/27. Some of these problems look intimidating, but if you break them down step by step, that's fine. And if you can do these problems in less steps, awesome. Okay, last problems. Let's simplify. So these are going to work just like they did last lesson, where I'm going to multiply. So 5 times 7, if I do those first, I get 35. And now I want to do the x's. So I have x to the half times x to the 3/4. And remember, when we do that, we have to add the exponents. Now last time it was a little easier because they were whole numbers. Now these are fractions. So off to the side here, I have to do 1/2 plus 3/4. To add fractions, if you think back to elementary or middle school, you need a common denominator. So the common denominator of 2 and 4, I can make this guy a 4. But that would mean I'd have to multiply by 2 to do that, so I have to times the top as well. So it becomes 2/4. I multiplied it by 2. Now I can add them together. So I would get 35x and 2/4 plus 3/4. I'd get 5/4. So 35x to the 5/4 is the answer. Let's do the next one. This time I'm going to divide. So 32 divided by 16 is 2. And then when I do the x's, when I divide, remember I subtract. So I'm going to have to do 5/3 minus 3/4. So off to the side. Oh my goodness, this stylus. I'm going to need a common denominator. Well, the smallest number that 3 and 4 go into would be 12. So to make this bottom guy a 12, I'd have to times by 4. So it would become 20/12. And to make this other guy a 12, I'd have to times by 3. So 20/12 minus 9/12, my answer would be 2x to the 11/12. And the last one, if I want to simplify this, oh my gosh, the 9th root of x cubed. Well, if this form is confusing, let's rewrite it as an exponent. So let's go backwards of what we were doing up here. So if I rewrite it back as a fraction, the 9 should be the bottom number, and the 3 is the top number. So now we can see, oh, 3/9, that would simplify to 1 over 3. Now let's write it back in radical form. So this one would be a 3, and then we'd have a 1, and really you don't even need to put that 1. So the simplified form would be cubed root x. So again, this whole unit is just a lot of simplification tricks that we will be using in the upcoming units. So that's all I have for this one.